So let's start our session, today's session. So first of all, I introduce myself. So good afternoon, everyone. My name is Rajat Boni. I am a PMRF research scholar at IIT ISM Dhanbad and also a teaching assistant at this course called Foundation Engineering, which is conducted by Professor Dilip Kumar Vaidya sir. This is week 5 of our uh, of this course, and in we already go through 4 weeks and also solve assignment problems of these weeks. And today is week 5. So in I have also 6 months teaching experience in NPTL as a teaching assistant. So this is my second course on NPTL as a teaching assistant. So, in this course, today's class, we will first try to discuss the 5 lectures of this week, and then try to solve previous year assignment problem, mostly 2020 assignment problems, and also discuss the or solve the class problem also, and if time permits, we also discuss the doubts of if you having any. So in this 1 or 2 points I mention here that this class is recorded and it will be shared to everyone in my YouTube channel, everyone from my YouTube channel, and whatever I am discussing here, the materials, it will be shared to you from my Google Drive. So, and one thing more that if a network issue will happen, then don't worry, I will try to join or very quickly to resolve this problem. So please let's stay on the line and let's start our today's session. So I'm sharing my screen. Please wait. I think it is visible to everyone. So I think it is visible. So let's start our session now. So so we are in now week 5. So week 5 there is 5 lectures. So one by one I am first discuss these theories or whatever uh, uh, given in this lecture. So we start with week 5 lecture number 21. So it is belongs to this lecture number 21 belongs to our previous class. That is called settlement of the footing. So in previous class we discussed about the different types of settlement of shallow foundation, that is elastic settlement, and for sandy soil, mostly for sandy soil, and pre-consolidation or primary consolidation settlement, which is mostly for clay nature or impermeable nature of soil. So, so in previous class, we mostly solve 1 or 2 question based on this elastic settlement. but uh, to and we discuss the preliminary consideration or primary consideration theory, but we don't solve any problem, or I think any we solve small problems but not big. So we try to solve one problem which is based on preliminary settlement or primary settlement. So first we discuss the primary settlement based on the degree of consolidation. So uh, we know that degree of consolidation depends on the time factor. So the time factor is nothing but one constant or factor which is it depends on coefficients of consolidation and time to take in the consolidation and thickness of the consolidated layer. So and we can say drainage path, the square of the drainage path. So if you see that the degree of consolidation if increases that from 0 to 100, time factor also increases, and it is a non-linear curve. And it is uh, depends on a term called M, which is nothing but the ratio of the pore pressure at the top surface to the ratio of the pore pressure at bottom surface. If top surface pore pressure and bottom surface pore pressure is equal, then this M is equal to 1. And mostly of our problem is based on our M is equal to 1. So for different M, small m, like m is equal to zero point 0.5, m is equal to 0, m is equal to infinity, the curve degree of solution, degree of consideration percent time factor will also vary. Then we can find out this time factor by using uh, two formulas based on the degree of consolidation. So this first one is if the time factor is equal to pi by 4 into degree of consolidation divided by 100 whole square. And this formula used when the degree of consolidation is less than equal to 60%. And then we can also use another formula for finding out the time factor, that is 1.781 minus 0.933 log 10 100 into log 10 100 minus degree of consolidation, and it is for degree of consolidation between 60 to 100%, that is u degree of consolidation, it is capital U is greater than 60%. Now we also this time factor is below depends on the coefficients of consolidation and the time taken for this consideration and for the drainage path. So to determine the drainage path of a clay of a layer where we find out this consideration, it is depend of the permeability or impermeability nature of the adjacent layer. So if this uh, if the layer is in a sandwich way is covering with both permeable layer. That means both side of this layer is both side of this layer present a to permeable layer. Then the drainage path, which is half of the thickness of this layer. That means if it is the thickness of the layer is h, then the drainage path becomes h by 2. It is because the actually the drainage path is the maximum traveled path by a water particle. So for if both side is permeable, the water is shipped either this direction or either this direction, dissipated either this direction or this direction. So the maximum travel path of a water particle is become h by 2, or half of the thickness of the layer. But if one layer is impermeable and another one is permeable of surrounding this uh, layer, where we find out this consolidation settlement, then this drainage path or becomes the thickness of this layer, because the maximum travel path of a water particle to dissipate is from here to here, because it is cannot dissipate it in this direction because it is impermeable in nature. So maximum drainage path become thickness of this layer, like this. Then here one problem is given based on this primary consolidation settlement. So it is very easy problem. So first we discuss this problem and try to solve it here. So it is said that a foundation is to be constructed at a site where the soil profile is shown. So one foundation is construction in layered soil. First layer is sand and gravel, second is clay, and third layer is again sand and gravel. And it is given the uh, unit weight of each layer. So the unit weight of soil at sand and gravel is given 19.8 kilonewton per meter cube, and for clay it is given 17.1 kilonewton per meter cube, and also given the thickness and height, depth of foundation, uh, thickness of the layer, and each layer. So we have to find out the settlement of this clay layer, which is happen. Actually, it is not given. It is not said that we have to find out the settlement and which layer. But by the question, it is said that we find out determine the primary consideration. So we know that the primary consideration is mostly happen in clay layer. So we have to find out the settlement in clay layer. So for this, we need one equation. We also discussed this equation in previous class. That is, uh, primary constant settlement is equal to Cc, that is compression index, into the thickness of this layer where we have to find out the settlement, plus divided by 1 plus E naught, that is initial void ratio, into log 10 sigma z dash plus del z dash divided by sigma z dash. Or sigma z dash is the effective stress at the middle of this clay layer, that is up to this much step, and del sigma z dash is the increase of pressure due to the construction of this foundation. So at the middle of this clay layer. So here the load given, which is increased due to the construction foundation, is 2000 kilonewton, and the foundation width is given, size is given 2.5 into 2.5 meter. So, and initial void ratio is given 1.1 and compression index given 0.60. And so we have to first find out the effective state at the middle depth and increase of pressure at the middle depth. So for increase of pressure, we use 2 is to 1 load dispersion formula at the middle of the curve. So we considered that the load dispersed as the 2 is to 1 ratio, and the 2000 kilonewton is act at the middle of this layer. And we have to find out this stress or pressure. We have to divide this 2000 kilonewton by the area, effective area at this layer. So it is become B plus D whole square, because it is square footing. So B plus D whole square. So D is nothing but the depth from the base of the foundation to the middle of this clay layer. So for and this is for 2:1 formula, and it is become del sigma z. And for effective stress, we simply calculate by formulas like gamma into or gamma dash into h. So I solved this question. So you can see the solution here. So you see that I first find out the sigma dash, which is nothing but 2 into 9.8, 19.8. That means uh, I rub it. Sigma z is 2 into 9.8 because it is above the water, 19.8 because it is above the water table, plus 2.5 plus 3.5 whole into 19.8 minus 9.8 because it is below the water table. So we subtract the unit weight of water, then plus 7 by 2 because we have to find out at the middle layer stress, find out the stress at the middle layer. So 7 by 2 into 17.1 minus 9.8, 81. So it is become our effective stress at the middle of air, which is nothing but 125.06 kPa. So uh, then we have to find out del sigma uh, sigma dash z, which is into load at the middle of the layer divided by B plus D whole square. So our D is 3.5 plus 7 by 2. So it is become a load is 2000 kilonewton, so it is become 22.16 kilo kPa. So all this value, if you put in so it is become 0.1353 meter, and if you convert it in it is become 135.3 So this is the solution of our class problem of lecture 21. So now we move on to lecture 22. So lecture 22 also given 22 in this lecture 22 also given same similar type of formula, and in this formula we have to find out one extra thing is the time taken for this degree of concentration 90%. If the coefficient of concentration is 4.96 into 10 to the power minus 6 minus 6 meters square per minute. So, and also in this formula, it is have to find out on the pre-consideration settlement of this clear layer. But in this question, CC, that is compression index, is not given, but pressure versus void ratio data are given. So based on this data, if you know that we already taught this, to find out CC, we have to draw void ratio versus log 10 pressure pressure of log. So if you plot, there's maybe one curve like this. So the slope of this curve is nothing but the CC. To find out the slope, if you take 2 points, mostly taking the last 2 points, so we can easily find out the slope of this curve. The slope of this curve, that is CC, is equal to change in void ratio of any 2 point divided by the log 10 pressure of ratio of this pressure of 2 point, P2 by P1. So if we put all this value of any 2 points, so we can get the CC. So after finding the CC, again you have to find the effective stress at the middle of this clay layer and also find the increased pressure due to this foundation at the middle of this clay layer based on 2:1 ratio load dispersion method. So after that, if all those things are uh, uh, find out, then we can easily solve or we can easily get the pre-consolidation by using this formula. Del C is equal to Cc into H divided by 1 plus E naught log 10 del sigma Z plus del sigma sigma Z plus del sigma divided by sigma Z dash. So put all this value after finding you can get this. So I am also solving this in my sheet. You can see that. So first find out the CC compression index. It is coming out at any 2 point slope of taking slope at any 2 points, which is not coming out 0.66. Then find out the effective stress at the middle of this clay layer, which is coming out 101.01 kPa. Then del sigma z dash, which is coming out 99.5 kPa. After all this, put this formula value, put all this in this formula and get the settlement. Frequency settlement is 91 mm. So our initial void ratio is given in this question is given here 1.8. We have to check before solving this question. So now we have to find out the pre-consolidation, time taken for 90% settlement, consolidation settlement. So for this, we have to use this formula TV, which is time factor is equal to CV, coefficient consolidation into time divided by drainage path square. So to find out T time, first we have to find out the time factor. We know that time factor depends on the degree of consolidation U. So we know that our degree of consolidation is greater than 60%. So we have to um, use this formula to get the time factor, that is 1.781 I think minus 0.933 log 10 100 minus degree of consolidation in percentage. So if you see my solution here, so it is coming out time factor is 0.848. So after this, put this in this equation. So before putting this in this equation, we have to calculate the drainage path. So in our problem, it is given that the this clay layer it confined in between two sand layers, sand and gravel layers, and above also in the below. So we know that sand and gravel layer is good for permeable, good permeable layer. So water can easily dissipate at this direction also, below this direction also. So our drainage path is become half of the thickness of this clay layer. So it will become 2.7 divided by 2. So we put all this value here and get the time in minute because our coefficient of concentration is given at meter square per minute. So it is coming in minute. After that, you can you can convert it either in hour or days or years. So I am converting it in days. It is coming at 216.38 days. So this is the solution of lecture 22 problem. So then we now we move to our lecture 23 of week 5. So, in week 5, lecture 23 is the new topic we have to discuss now, which is nothing but the geotechnical investigation. So, I also call soil, also we can call soil investigation. So before going to build anything in this any type of soil of existing soil in the or uh, in your construction site, we have to first find out the behavior and nature of this soil. So for this, we have to investigate by different types of method, by different types of empirical formula, and get specific result, engineering properties like or index properties. After this, we calculate the strength of this soil. So for this, we have to need the soil investigation before our construction. So it is the most important uh, chapter with in respect of in the point of view of or in the viewpoint of geotechnical engineering. So in this we have to set first some goals why we want to in this geotechnical investigation or you can say soil investigation. So our goal is to estimate the geometry of soil strata and to find out the groundwater table. So what type of soil is below on the ground surface, below the ground surface. Either it is sandy soil or clay soil, we have to find out and also find out the depth of water table below the ground surface by this soil investigation method. Also, the field investigation identify the material or layering and retrieve the samples and engineering properties through the in situ testing. So, some instrument by using some instrument like SPT cone penetration test in in the field, we can also find out the different engineering properties of the soil and try to address uh, the different parameters or get the different parameters by this soil registration method. And also conduct some laboratory test based on this or based on this sample which I collected from this site. We also uh, we, this is also our goal in soil investigation. Then now it is site recognition. So site recognition is the first visit of this site to uh, by an experienced professional to collect the first-hand information like geology, terrain, and equipment access, uh, existing structure and their condition, existing utilities, and potentially hazard conditions. Now we have to fulfill the checklist where in our site recognition. So in site recognition, when we visit, when a professional, experienced professionals visit the site, they have to examine the exposure of soil and rock in carts like highway roads, then also in building excavation, gravel pits, steam banks, and on the surface and the not influent ground water seepage. They also examine the slope for sign of instability, examine the existing structure and pavements for sign of distress, to note the evidence of flood levels along the stream. Again, they have to contact the local well drillers for the information of groundwater condition, contact the local public official for building code data and information on the foundation and soil condition. Also note the soil condition imposing the constraint on access of exploration equipment. So these are the checklist. These are the fact points they have to maintain or mm, they have to examine when they go for site recognition. Then, after site recognition, they go for detailed deck study uh, prior to the field investigation. So, in this, they uh, they examine the air photos of vegetation, water depth, then also examine the ground color of soil rock and types, slides and fault. Also examine the maps of topographic maps, geologic maps, the rock types on surface, deposition of soil, geology, and also examine the nearby structure and go through the literature which is previously published based on this type of soil and some local knowledge also they have to get in for deck study. After that, they have to plan the subsurface soil exploration. So this subsurface soil exploration uh, occur in three steps. One first is boring, then sampling, then testing. So in boring, refer to the drilling uh, or advancing a hole in the ground of a diameter 75 to 600 mm. And sampling refer to the removing the soil from the hole. And testing refer to the determining the characteristic of properties of the soil. So then that they have to determine before going to subsurface exploration, they have to determine the number of boreholes, borehole spacing, location, depth of borehole, and also determine the types of sampling device, sampling interval, additional in situ test, relationship between with the laboratory testing program and instrumentation. So all these things they have to plan before going to uh, or subsurface exploration or detailed exploration, detailed subsurface exploration. So now in borehole pacing, it is mostly depend on the project and surface condition. So for building, approximately the spacing between two borehole approximately 15 meter or sometimes 50 meter apart in both direction. Focus on corners and key interior location. That means if one square plan of a building is given, our spacing should be interval or borehole spacing should be at a 15 meter or either at the corner of this building plan uh, at the four corners and one should be at the center of the this building. Then for site development, we need to bore hole for every 50 to 150 meter apart for preliminary studies. Then for soil wall or cut, we have to need a borehole every 30-meter interval. For earth dam, we need 60 meter across the foundation. For road, it is become 100 meter for every interval. Then we need to find out the borehole depth. So it is also depend on different types of structure. So in buildings, the depth where the vertical pressure is less than the 10% of the pressure at the surface but not less than the 10 meter for the soil and 3 meter for the rock. If the soil strata exists, go deep enough to define the geometry. That means for building, if you build one building above a soil layer, the depth of boring should be at a depth where the pressure stress, vertical stress is the 10% of the vertical stress at the ground surface. That means for this building, there may be generate one load on the ground surface, and for by this load, stress will develop at this ground surface. So our depth of borehole should be at a depth where the stress become 10% of this stress of the ground surface, or 2 to 3b from the ground surface. That means 2 to 3 times of the width of the foundation from the ground surface. But the depth of this borehole should not be less than the 10 meter for soil and 3 meter for rock. But if any soft soil strata exist in between these, so go deep enough to define the geometry. That means if any substrata exists, so you have to uh, go through this substrata to find out the thickness of this substrata. Then for cuts, the depth of borehole is 3/4 of 4 to 1 times of the base width of this cut. For excavation is 2 times of height or 2 times of width of the excavation. For depth, arch the depth, it is half times of the base width of this arch depth. And for pile, it is 3 to 5 meter below the pile tip. So these are the condition depends on different types of structure to find out the borehole depth. Then sampling interval. So we have to find out sampling uh, at every stratum or for every 1 to 3 meter depth, and typically every 1.5 meter observe cutting or sample more if necessary. So if we observe the cutting and we have to need more sample, so we need to take every 1.5 meter depth sam to collect the sample. So now boring and sampling. So field engineer should record all the relevant information: time, date, weather, type of equipment, casing used, drilling mud or dry, depth at which water table first encounter, loss of drilling fluid, water level at the end of the boring, and anything. So this is called boring and sampling. Now we move on to lecture 24. So in lecture 24, it is the continuation of lecture 23. So here we have to study the boring equipment. So different types of equipment used for boring, and it is depends of the importance of the project or the height of the boring. So for shallow boring, we need shallow boring or small projects. We need hand auger. So these are the different types of hand auger. So one is called post hole auger, another is called helical auger, and This is called extension rod. Then there is another instrument called track mounted auger, and this is good for when above the water table in sand, silt, and clay. But if you use this in soft soil or below the water table, then there may be collapse of the soil. So this may be risk. There may be risk for using this type of auger in below the water table or soft soil. Then wash drilling. So most condition requires track or drill rig and water for drilling mud. And this is used for most type of conditions. Sorry for that. Now rotary washed drilling equipment. So a cutter here, a cutter bit or a core barrel with a coring bit attached to the end of string of drill rods is rotated by a powering ring. So by this way, this type of rotary was drilling worked. Then there is percussion drills and wireline drilling. So wireline drilling is used for deep holes and offshore drilling, and percussion drilling used for gravel or soil with boulders casing used to support the hole and prevent the caving. Now sampling equipment, which is also called sampler. So for disturb samples, we use thick wall sampler, and for this and this is used for routine jobs to identify soils and determine the index properties. And most common sampler for disturb sampler is split barrel SPT sampler, and there is another one agar sampler. So here it is one picture is shown for SPT sampler. So these are the different types of cross section is shown for SPT sampler. So you can go through it. There is then there is undisturbed sampler, and it is used for more complex jobs and for where the clay exists, and sample used for laboratory testing for strength to find out the strength and consolidation. So this type of sampler or undisturbed sampler mostly used for the clay and mostly used for complex job, and find out mostly by this sampler we can use to find out the strength and consolidation of the soil. Then there is requirement of sampler for undisturbed sample. So this undisturbed sample depends on different types of factors or terms. One is called area ratio, another is called inside clearance ratio. And here it is given the formula to find out the area ratio. Here d naught is the outer diameter of the sampler, or di is the inner diameter of the sampler. So for well designed sampler, the area ratio should be less than 10%. It is area, not R. Area ratio. Area ratio should be 10% or less than 10% for undisturbed sample or sample. Then there is different type of sampler or undisturbed sampler. You can say one is hydraulic piston, which is a thin walled or shelby tube pushed ahead of device. Then pitcher or Denison barrel, a hard dense soil removed by advancing uh, while cutting. Then a sampler called hand cut block samples, which is has highest quality, which is highest quality but most expensive, only retrieved from the excavation. Then there is time in situ testing. So in situ testing is called the test of the soil sample at the field. It's called in situ testing. So for in situ testing, we mostly used SPT, CPT, or, or geophysical uh, methods like electroresistivity method, MSWS method, Venn method, like this. So this in situ test is extensive use and especially is used for ground improvement evaluation to evaluate the ground improvement method. Then there is advantage and disadvantage of this in situ testing. So the advantage is it is used in soil that cannot sample easily. Then test in correct environment and continuous profile we can get by CPT and also cost effective. And there is also disadvantage that no sample for identification, some unknown test conditions, need empirical correlation, and test only current conditions. So these are the disadvantages. So it is also completed lecture 24. So now we move on lecture 25. So before starting the lecture 25, now we take 5 minutes break. After that, we continue our session. So please stay on the line. I will join after 5 minutes. So please stay on the line. Welcome back to this foundation engineering class, week 5. So we now we just completed lecture 24. Now we start the lecture 25 of week 5. So in lecture 25, there is given the benefits or use of uh, SPT test and why using SPT test in our soil investigation. So it is said that it is the oldest and most widely used method and good for most type of the soil. So different types of soil we can use this SPT test. So that's why we can use readily or we can use widely this SPT test. So useful for correlation like to determine the angle of internal friction of the soil, determine the relative density, also determine the Young modulus of the soil by this SPT by a number. Then we also standardize our SPT number, that is the SPT number is the number of blows per 300 mm depth of penetration using 65 kg hammer falling from 750 mm. So height of falling is 750, hammer weight is 65, 750 mm, and hammer weight is 65 kg. Then sampler is 600 mm long, and the outside diameter is 50 mm, 50 mm, and inside diameter is 35 mm. and also requires some correction because it is manually uh, we can do this SPT test. So there may be uh, human error, or there may be load inclination error. Also, that soil is given some resistance by some presence of some boulders. So we have to correct our SPT number by different methods. So one thing we have to mention that the first 300 mm, oh sorry, uh, the first 150 mm data we have to neglect because it is given the topsoil data, and most of the topsoil is the topsoil at 150 mm. We think that it is mostly variable, very rapidly, so we neglect 150 mm top surface data or number of blows. Then here is the methods are shown in picture how we do our SPT test. So it is doing by manually. One sampler is inside into the ground. Uh, then after that, one hammer is free fall at a height of 150 mm, sorry 750 mm, uh, and the hammer weight is 65 kg, and it is free fall on the sampler, and sampler is pushed into the ground surface, and we need to calculate, we need to observe that number of blows for every 300 mm penetration. So after that, this is our SPT number for each 300 mm depth. If the number of blows are more, that means the strength of the soil is very good. If it is less, then soil is, we say this soil is very soft. So here picture is shown of our sampler. So the uh, inside diameter, we see that inside diameter is 35 mm. The sampler inside diameter is 35 mm, outside diameter is 50 mm, and the length of the sampler is 65 mm. Then we need to correct our SPT number, and the correction is for hammer efficiency because the total load on the sampler may not be transferred due to some inclination of this hammer or some uh, reduction or radiation of the energy. Then we need to correct also borehole diameter. Also, we need correction for sampler because sometimes there may be error of to create the sampler, adjust the sampler. So we need to also one correction factor for sampler. Also, we need to correction factor for rod length, and most important correction is for overburden pressure. So overburden pressure, which is depend on the effective stress from the ground surface. So here the overburden correction is called Cn, denoted by Cn, which is nothing but root over 100 divided by sigma dash. Sigma dash is the overburden, so effective stress, and this unit should be in kPa. That means kilonewton per meter square. So by this formula, we can find out the corrected SPT number for each layer. One problem we also solved in our upcoming lectures. So now we have to find out the correlation between this SPT number for different types of engineering properties like relative density and internal friction of this angle of internal friction of the soil. So if the SPT number is in between 0 to 5, So our degree of or relative density is in between 0 to 5%. This is the scale is percentage is in percentage, and our uh, angle of internal friction is 26 to 30 degree. So this unit is degree. Like this way, if our SPT number is in between uh, 30 to 50, then our degree of relative density is 60 to in between 60 to 95, and and our internal angle of internal friction is in between 38 to 46 degree. So you have to remember that if our SPT number is less, then the soil is called soft soil. If or soft soil or loose soil, soft soil for clay, loose soil for sand. And if our SPT number is high, that is 30 to 50, then the soil is called very stiff soil for clay and very hard soil for sand. So from here to here, actually the strength of the soil get increased. So means if the SPT number is high SPT number, that means higher strength of the soil, and also higher angle of internal friction. Also, the relative density also higher. Then the correlation between this Young modulus and the SPT number for cohesionless soil. So for non-plastic silt sand mixture, the Young modulus is 400 into n means SPT number, and unit is kilonewton per meter square. But if the unit is ton per foot square, then this is become 4 into 4 times of n means SPT number, and here it is mostly for corrected SPT number, n corrected. Then for clean sand to medium sand, it is become 700 times of n. For coarse sand and with a little gravel, it is become 1000 times of n SPT number. For sandy gravel, it is and only for gravel, it is for 1200 times of SPT number. Then then there is the correlation between the consistency and unconfined compressive strength of the soil based on the SPT number. So if the SPT number is in between 0 to 2, our unconfined, it is called very soft soil, consistency soil, and our unconfined strength is in between 0 to 25. Like this way, if our SPT number in between 20 to 30, it is called very stiff soil, and our unconfined compressive strength is in between 200 to 400. If our SPT number is greater than 30, it is called hard. Consistency is hard, and it is the compressive strength is greater than 400, and all the units of the uncompressed strength is in kilonewton per meter square. Now there is one geotechnical investigation test which also most popular, which is called cone penetration test, and this test is newer method and good for developing the profile, that means continuous profile, but do not get sample. So in concentration test we cannot collect the sample from at a depth from the ground surface, but we can find out the properties of by this instrument as a continuous basis from the ground surface, and this test is faster and less expensive than the drilling and SPT, and used in conjunction with SPT, and the measures friction and cohesion, also can measure pore pressure and shear velocity with piezo cone. Now one problem is given to find out the corrected SPT number, and condition is given that the depth of water table is at 30 water table at 3 meter from the ground surface, and the unit weight of the soil above the water table is given 17.5 and below the water table is given 18.5 kilonewton per meter cube. So we have to find out the corrected SPT number for this condition, and most of the correction is here, it is for overburden correction. So in our problem we have to find out only for overburden correction. So for this overburden correction, which is nothing but Cn is equal to root over 100 divided by sigma dash. Sigma dash is nothing but the effective stress at a particular depth, where we have to find out the corrected FCT number. So first we need to find out the effective stress at a particular depth, then calculate the Cn for overburden pressure, and this unit should be in kPa, and after that you multiply the field value SPT with this Cn, we get the corrected SPT number. So add for each depth. So I solved this question in my sheet. You can go through it. So you see that one problem I detail for one layer. First layer I solve it in details. So you can see that first I calculate the effective stress at depth of 1.5 for first layer. Then after that we calculate the corrected SPT, correction SPT correction for overburden, which is coming out 1.94. Then multiply it with the field value SPT number, that is 12, and it is become 23.38. So we can take only the lower whole number for every case. So if our value is coming out like 23.38, we have to take 23, the lowest whole number. If it is become 23.98, or we can say 78, we also take 23, the lowest whole number. So for first depth, at a depth of 1.5, our SPT number is the characteristic number is become 23.38, and we can take it 23. For at a depth 3, it is become 19.22. We can now take 19. Like this way, at a 4.5, it is become 19.76. We take 19, and in this way, we find out the characteristic number for different depths. So now we move on to the assignment problems. So first we solve the 2020 assignment problems, week 5 assignment problems. So one by one, now we can solve these assignment problems. These questions are very easy. If you try, then easily you can solve it. So I am discussing one by one. So the first question here, it is given that undisturbed soil sample are required for conducting what type of test? Consolidation test, plastic limit test, hydrometer test, or specific gravity test. So the specific gravity, hydrometer, plastic limit, these are not required the disturb. Uh, these are not required the undisturbed sample. We- so in disturbed sample also we can find out this type of cell. So only consolidation test, we replicate the soils, find out the consolidation of a soil sample. For this, we replicate the soil condition, and we need the undisturbed sample for this. So our correct option is option A. Then wash boring. Then question number 2 it's given that wash boring is not suitable for. So if you remember, in different types of equipment in lecture 24, wash drilling or wash boring. So if wash boring actually worked with the principle of high water pressure. So in rock, if we apply, if the soil it is easily useful for cohesive soil, also useful for cohesionless soil, but it is not useful for gravel and boulder soil with mixed with gravel and boulder, because in wash boring we use the water pressure to drill the borehole. So to drill the borehole, we if the surface of the soil, if it is hard, then there is no meaning of applying the high pressure water. So if the soil mixed with the gravel and boulder, it is difficult for the wash boring technique. So our correct option is option C. Then the question number three, move on to question number three. The question number three is asked that the observed standard penetration value in a deposit of fully submerged sand was uh, 45 at a depth of 6 meters. The average submerged unit weight of soil is given 9.7 kilonewton per meter cube. We have to find out the corrected SPT value. So our field observed SPT number is given at a depth of 6 meter is given 45. So we have to find out the corrected SPT number due to the overburden pressure. So first we have to find out the effective stress at a depth of 6 meter. If we consider our ground surface, this is our ground surface, and our SPT is, we have find out our SPT field observed value at a depth of 6 meter, it is 45, and a submerged unit weight given, that means gamma dash is given 9.7. The gamma dash is nothing but the gamma saturated minus gamma W. So already here it is given gamma submerged value 9.7 kN per meter square. So first find out the effective stress, which is sigma dash is equal to 9.7 into 6, which is coming out. I also solved this question here, which is coming out like 9.7 into 6, 58.2 kilonewton per meter square. You have remember this. This unit should be in kilonewton per meter square. After that, now we have to find out the correction factor for overburden pressure, that is Cn is equal to root over 100 divided by sigma dash. Here sigma dash is equal to 100 divided by 58. Sigma dash is 58.2. After calculating this, it has become 1.31. 1.31. So then we have to multiply this Cn with our field observed SPT number to get the corrected SPT, that is 1.31 into 45, and this value become 58.98. So our correct option is here option D. So it is 58.95. So we found out 15.98. So almost equal. So our correct option is option D. Then we move on to question number 4. So it is said that for an undisturbed soft sensitive clay sample, the area ratio of the sample should be. So it is option A given 0, B is 10% or less, C is given 10% to 20%, and D is given more than 20%. If you remember, the area ratio is formula of area ratio AR is equal to D naught square minus DI square divided by DI square into 100%, where D naught is outer diameter of the sampler, DI is the inner diameter of the sampler. So for undisturbed sample, this difference square of this difference should be minimal, and for this it should be in between 10% for undisturbed sample. That means our area ratio should be less than 10% or 10 for getting the undisturbed soil sample. So our correct option is option B. So if this difference is greater than 10%, there may be come resistance while collecting the uh, sample by this sampler. So due to this resistance, because the thickness of this sampler become more, because the difference is become more, so due to this collection, there may be get disturbed. The sample may get disturbed due to this resistance. So our aim is to make a sampler should be like that, where the area ratio should be 10 or less than 10. So our correct option is option B. Now, one question is given, and one at 5 one table is given for different depth, sampler penetration, and different SPT number. So we have to find out the field value SPT number. So here the table is given in question number 5. SPT number given for a depth profile for a different layer. So from, if we consider here it is 0, from the ground surface is at 0, from at a depth of 150 meter, 150 mm, SPT number is 9, and next layer, next 150 mm, the SPT number is 11, and next 150 mm, the SPT number is 30. So if you remember, I told you that we have to neglect the first 150 mm result, because in this it is the upper soil layer, So in where the variability of soil is more, so we have to neglect this layer SPT number, and the standard value of the SPT number is the uh, number of blows per 300 mm depth of penetration. So if we add 150 and 150, it becomes 300 mm. So our we should also add this SPT number 13 plus 11. So it become 24. So our corrected answer is option C, which is 24. Now I think it is okay to everyone to understand this problem. So here nothing is I'm uh, this question is very simple. We have to neglect the first 150 mm result. Then we have to add next to 150 mm result, layer depth of layer result, because our standard SPT value is uh, number of blows per 300 mm depth of penetration. Then now in question number 6, so it is matching two list given, which is for construction with the appropriate borehole spacing. So, we, if you remember in lecture 20, I think yes, lecture 23, we go through the spacing of borehole, spacing interval for, sorry, yes, spacing of borehole. So for building, it is 15 meter. For site development, it is 50 to 150 meter, 150 meter. For soil wall or cut, it is 30 meter. For earth dam, it is 60 meter. For road, it is 100 meter. So go back to our question. They said that for road. So we know that it is 100 meter interval. We have to, the spacing between two borehole is 100 meter. We know that for earth dam, it is 60 meter, and for residential building it is 15 meter, and for soil cut it is 30 meter. So I think it is correct. Again we have to check. Yes, earth dam is 60 meter, soil cut is for 30 meter, road is 100 meter, and for building is 15 meter. So our correct option is, so I is equal to a, sorry, 1 is equal to a, 2 is equal to b, 3 is equal to D, and 4 is equal to C. So correct option is A, B, D, C. A, B, D, C. So correct option A. So now, so it is a memory based question, or question number 6 is based on the memory based question. So for this, we need to remember all the interval value for different types of project, and also all the uh, for this type of question we have to remember the all the interval value, spacing value, then result taking interval value, like depth of penetration value, at what depth we can collect the sample, and depth of borehole value for different types of project. We need to remember to solve this type of question. Then the question, we move to question number 7, which is based on the borehole depth. So we have to remember all the borehole depth for different types of project. So here it is given for find out the depth of borehole for earth depth. So if you remember, or we can also go back to our lecture number 23. Here it is given for different types of uh, projects, the depth of borehole. So building, it is the depth of borehole is not less than the 10% of the pressure at the surface, or the two times or three times of the width of the foundation, but not less than 10 meter for soil and not less than 3 meter for rock. And for cuts, it is in between 3/4 to 2 1 times of the base width of the scarp. For excavation, it is in between 2 times of height of the excavation, or 2 times the width of the excavation. For piles, it is 2 to 3 meter below the pile tips. And in our question, it is set for earth return, which is equal to the half times, 0.5 times of the base width. If that means if we construct a dam, earth dam, the width is, we can say, B, then our depth of borehole should be zero point 0.5 B. So our correct option is option D, half times of base width of the dam. Now we move on to question number 8. So we have to remain solve another question 5, 6, 7 questions. One, 5 questions are remaining. So we move to question number 6. Here it is said that, sorry, question number 8. It is said that 67 mm is the external diameter of the sampling tube. Uh, Find out and given the area ratio 11%. So we have to find out the thickness of the sampling tube. So for this, we put first find out the internal diameter of the sampling tube. So we can use the area ratio formula, which is equal to d naught square minus di square divided by di square into 100%. So area ratio is given 11%, and di, that is outer diameter, is given 67. Uh, so it's square, di square divided by di square equal to 11 by 100. We move 100 left side. So after this, multiply both side. So it will be 67 square minus di square equal to 0.11 di square. After that, di square is 1.11 di square is equal to 67 square. Di after that, di square is equal to 67 square divided by point 1.11, and di is equal to root over 67 square by 1.11. It will come become 63.6 mm. Now, if you draw the cross section of a sampler like this, the outer diameter is di, which is equal to 67 meter, and inner diameter is di, which is 63.6. So the difference is 67 minus 63.6 equal to 3.4, which is equal to the 2 times of the thickness T, because the difference is coming out this thickness plus this thickness. So here it is T, here it is also T. So 2 times of T is equal to 3.4. If you divide 2 by 3.4 by 2, so it is come 1.7. So our thickness is sampler is 1.7. So correct option is option A, 1.7. Now I think it is okay to everyone. So now move on to question number 9. In question number 9, I think in question 8 should be understandable to everyone. So it is nothing but simple calculation. We have to find out simple geometric calculation to find out the thickness of the sampler in mm. So now we have to find out the solve the question number 9. So in question number 9, it is said that the saturated clay stratum draining both at the top and bottom undergoes 40% consolidation in 16 years under a applied load. If the if an additional drainage layer were present at the middle of the clay stratum, 40% uh, consolidation would occur in hot air. So in both the case, the consolidation is same and soil also same. So our TB is equal to same, TB also same. That is time factor also same because our consolidation degree of consolidation also same. It is also the same soil used. So our coefficient of consolidation also same constant. So if you know that TB is equal to CV into T time divided by the drainage layer thickness square. So in our case, TB same because concentration same, CV same because soil also same. So time is proportional to thickness layer of the square of the thickness of the layer. So in our case, it is said that one clay stratum is present. So our drainage is and draining in both the way. Here it is in this direction also, in this direction also. So the height of the drainage layer become or thickness of the drainage layer become h by 2, half of the thickness of the clay layer. But in the second condition, it is said that we divide, we put one drainage layer in between the clay layer. So the thickness of the clay layer become h by 2. Here also h by 2, and this drainage layer also a porous layer and draining also occur in this direction, also occur in this direction. So our drainage layer become half of the thickness of the new clear layer, which is equal to h by 2 divided by 2 equal to h by 4. So if you now using this equation, that is T proportional to h square, and if you write like this, T1 by T2, which is equal to h1 square by h2. So if you consider T1, we need to find out our T1 is the year we need to find out. T2 is 16 year. So H2 becomes H by 2 square. H1 become H by 4 square. So if you write here like this, T1 is equal to 16 into H by 4 square divided by H by 2 square. You cut H 2 2, then it is come 16 by 4 equal to 4 years. So our correct option is 4 year, option C. So our correct option is option C. I think everyone should understand what I am discussing here. So it is nothing but we can, if we put our one drainage layer in between, so the drainage path become half. So if you put this, you can use if a t proportional to h square equation, so we can easily find out the time taken for consideration if we put one new drainage layer in between. So it in our common sense that if we increase the drainage path, or if we increase the drainage layer to dissipate the water very quickly, so our time also required for consolidation less. So correct option is option C. Now move on to question number 10. Similar question I also solve in our today's class in lecture number 21 and 22. So I can also again solve it here, question number 10, and question number 11 and 12 is linked with the question number 10. So please first understand the question number 10, and then we can solve the question number 11, easily solve the question number 11 and question number 12. So in question number 10, it is said that a footing is to be uh, constructed 2 meter below the ground surface as shown in figure below. The base of the footing is 1.5 meter by 1.5 meter, and it carries a total load of uh, 1 1500 kilonewton. The increased pressure at the middle of the clear layer because of the footing load based on the trapezoidal dispersion, that is 2:1 dispersion load dispersion method, we have to find out. So increase pressure, we need to ask for find out the increased pressure at the middle of the clear layer when the load dispersion in a trapezoidal way at a at 2:1 ratio. So vertical is 2 and horizontal is 1. That's a ratio of 2:1. So for this, we, that means our load is coming, total load is act at this middle of the layer, which is 150 uh, uh, 1500 kilonewton. So for to find out the increased pressure, we need to find out the size of this or width of this trapezoidal at the middle of this depth. So which is nothing but B plus D up to here. I'm drawing it again very. So the load distribution is 2 is to 1 here, also here. At the middle of the layer, load act is 150, 1500 kilonewton. Ratio is 2 is to 1. And at 2 is to 1, the width at the middle of the layer is B plus D. B is the width of the foundation where it is given 1.5 meter, and D is the depth from the base of the foundation to the middle of the layer, which is D, which is equal to 2 plus 3 by 2. 3 is the thickness of the clay layer, which is equal to 3.5. So our del sigma z dash is equal to 150, or we can say in general form we write q by total load by q by b plus t whole square. Because it is square footing in both direction, the width of this trapezoidal load dispersion trapezoidal is same. So it is we write b plus this whole square. So put this value at q, it is put 1500, b is 1.5 plus 3.5 whole square. So it is become 5 whole square 25. So 25, 150 divided by 25, or 1500 divided by 25, it is become 60. So our correct option is option D, in kPa, uh, 60 kilonewton per meter square. I think it is understand to everyone. Our correct option is option D. Now move on to question number 11. We also short running short in time. So in question number 11, this said that to find out the expected settlement of the footing because of the consolidation of the clay layer. So indirectly it is said that to find out the primary of the consolidation settlement of the clay layer. So for this, we use this formula. Del is primary consolidation settlement is equal to CC compression index into thickness of the clay layer divided by 1 plus E naught initial void ratio into log 10 log 10 sigma z dash plus del sigma z dash divided by del sigma uh, sigma z dash. So first we find out the sigma dash, that is effective stress at the middle of the clay layer from here to here, so which is equal to our water table is at this step, so which is equal to 2 plus 2 into 17, because we our which it is above the water table, plus 3 by 2 at the middle of the clay layer into the 20 minus 9.81. So it is the subgrade unit weight of the soil, 20 minus 9.81. So it is become 4 into 17 plus 1.5, that is 3 by 2, 1.5 into 20 minus 9.81. which is equal to 83.83. Our sigma z dash is 83.285 kilonewton per meter square. Now, to solve this, we need to find out the compression index, the CC. So we know that here, but here CC is not given, but liquid limit is given, which is equal to 45. We know that CC is equal to 1 empirical formula is no CC is equal to 0.009 into WI, this is liquid limit minus 10. In our case, liquid limit is 0.009, liquid limit is 45 minus 10. So CC is 0.315. So CC is 0.315. Now put all this value in this equation and get the result. I rub it. So put all this value. Del sigma C is equal to CC is 0.315. Depth of the thickness of the clear layer is 3. H is 3. 1 plus initial void ratio is 1.3. Log base 10, and the, sigma z dash is 83.285 plus our increased pressure del sigma z is 60, which is found out in question number 10, divided by sigma z dash is 83.285, which is equal to, which is I am solving here, which is equal to uh, 96 0.09681, which is equal to 96.81 mm. So our correct option is for question number 11 is option A, which is 96.81 mm. Now, our last question in our session, also in our assignment, also in our session. So after that, we close our session. So this is the last question, very, which is very simple to solve. So this question also linked with question number 10. So in here, you have to find out the number of days required to reach 50% of degree of consolidation of the clay layer. So we have to find out if the coefficient of consolidation is given 0.008 meter square per day. So our answer will become in day, because our coefficient of consolidation is given in meter square per day. So our time also coming out in days. So for this, we have to first find out the time factor. So to find out the time factor, which is depend on the degree of consolidation, and in our case, the degree of consolidation is 50%. So we use this formula, first one, where TV is equal to pi by 4 into u means degree of concentration divided by 100 whole square, because our degree of concentration is less than 60%. So put u in this equation as 50 divided by 100 whole square, and it is become 0.19625. 0.19625. Our TV is equal to 0.19625, and then use this equation to find out the time, which is TV is equal to time factor is equal to CV into T divided by H square, where H is the thickness or length of the drainage path. So go back to the question number 10. So the length of the drainage, to find out the length of the drainage path, we have to evaluate the condition of this clay layer, and above and below there of the clay layer there is present sand and gravel. So we know that sand and gravel is very good for the permeability, good have good permeability. They're called permeable soil. So water can dissipate in this direction also, water can dissipate in this direction also. So our drainage path will become half of this, the thickness of the layer, that means divided by 3 divided by 2, that means 1.5. So our drainage path length is 1.5 meter. So put all this value here. CV is given already 0.008, and H is given, find out is 1.5 whole square. H square is 1.5 whole square, and TB calculated as 0.19625. So, and we have to find out the T as in terms of days. So put all this below and calculate 0.19625 into 1.5 into 1.5 by 8. So it is coming out, T is coming out about 55.19 days. So in our question, the nearest option is option number C, 55.22 days. So our correct option is option C. So I think it is understand to everyone how I am solving this question. So if a similar type of question is given to your assignments in this year, so please try this question first. Previous assignment problems. I also share this to my Google Drive. You can access it, and also this section, video is recorded. If you have any doubt, go through my video also in my YouTube channel. I am also uploading this in my YouTube channel. So now I'm stopping here. Stop here. So we can meet again in uh, next week, which is week number 6. So you try to solve this question. I am also sharing the previous year 2023 question also. You can also try to this question also, uh, those question also. So now I am stopping here. It is already 5 p.m. So I am stopped now. So best of luck, and thank you to everyone. I'm stopped now.